welcome to the last talk of this track, I guess. My name is Ekin. I'm a data scientist specialized in privacy-enhancing techniques in deep neural networks who needed to manage a Kubernetes cluster once, and here I am. So it was quite a journey. I recently joined NVIDIA following the RunAI acquisition. And at RunAI, we are building the software for orchestrating AI workloads and GPUs at scale for enterprises. And we have customers from all sorts of companies, from education, from financial institutes, defense, healthcare, etc., that are using RunAI platform at scale. So for the platform, years ago, we needed to create a scheduler around in 2019 or so. So we needed to build our own AI workload scheduler because of the reasons that I'll explain in a second, and made it open source and donated to CNCF last year in KubeCon London. Now Kai is a CNCF project, and today I will basically share the challenges we had while creating Kai and why we had the need to create a scheduler from scratch. So let me introduce you how a cluster looks on a regular day in those teams. So one pool of resources, if you are lucky, you have. Otherwise, some teams might have under desk GPUs, etc. So we are assuming the good case scenario here. There are a bunch of teams. I dropped some names, but they can be named differently, like researchers, pre-training, post-training, data scientists, ML engineers, etc. They have different deadlines. Everyone thinks that their job is the most high priority. Everyone thinks they should be first in the queue when they submit something to the cluster and they want to get as much resources as possible. And everyone has different types of workloads, right? So they have training workloads, they have inference workloads that are seeing customers, and they have very strict SLAs. They have interactive sessions where they want to debug stuff in a terminal or VS Code session, etc. So they just want access to this cluster with all these types of workloads. So how can you, as an admin, make all of these people happy, accommodate all those types of workloads in a dynamic way while not breaking the bank? So we have been asking this question to ourselves for a long time. And today I will basically talk about that process that we went through for years in 30 minutes. So I will first explain why AI workload scheduling is getting so tough and what has changed with time. The gaps that we hit, like the main ones, we hit a lot of gaps, but I will just check the main ones, how we close those gaps with Kai's scheduler, and I also want to give a quick overview on what is happening in the upstream, because there is some exciting news happening right now that will land or are landing while we are talking, and some key takeaways. So let's get started. Before we blame any scheduler, let's look at what we are throwing at it, okay? So in even 2020, I should have corrected that. A big job was 8 GPU training job. It was complicated. And now we are seeing disaggregated servings, agentic pipelines that need scaling in multiple levels, multi-node NVLink fabric that you need to manage within your cluster. So there are different types of workloads that are growing and growing in demand as well from the scheduler point of view. So the scheduler didn't get worse, or it was not something that we created and actually didn't address the problems. The homework just got 10x harder. The good news is we are on it, and we are not alone. So Kai is one of the schedulers in the community. There is also Volcano, Q, Unicorn. You probably heard some of them. So everyone is working towards solving some of these problems with their own way, with different design ideas, and with different focuses. So before I go into the tricky part with scheduling, I want to give you an overview what we are scheduling. So you can basically divide the types of workloads into 3 main domains. The first one is the interactive session that I mentioned, basically a researcher going to a VS Code, PyCharm kind of IDE or a terminal session and checks out some does some decoding or checks out some data analysis, etc. These start instantly. They are idle for hours because I wanted to get a coffee, and then I came back, but I didn't want to leave my instance, go to someone else, so I kept it on. And they could use a slice of a GPU. These are not memory-heavy workloads, so you can use DRA, GPU sharing, fractioning techniques, etc. here. In training, we have a bit more complicated workloads. These can be single, multi-node trainings with model parallelism, data parallelism, or both. They can be huge RL, pre-training, or post-training workloads. So these are long-running or hero jobs, we also call them. All or nothing or gang scheduling is a must-to-have. And these workloads can be elastic, so you can expand and shrink if it's needed. They are topology sensitive because of the throughput that you need, and you can preempt them because we are checkpointing while doing the training. So if there is an inference workload that's more important, you can preempt the training workload and make space for inference. So then you can basically restart the job once the inference is done. And in inference, this is the most important one. It's basically seeing customers, real-time inference, disaggregated serving, agentic pipelines, etc. are all falling into this category. Highest priority. It's latency bound. Super important that they are scheduled as in the correct topology. And we also started seeing hierarchical gangs, multi-level scaling for those workloads, which makes things harder. And so these are the workloads that all of those teams, each of these teams, can submit at any time of the day, of the week. And as if this was not enough, as if this was not complicated, we are making things even more complicated. As a data scientist, I think I can say that. So we started having some more gangs of trees. So for example, this is an RL post-training architecture, and this is this disaggregated serving architecture. In the RL post-training, we have a trainer on GPUs, a rollout server on GPUs again, but it can elastically expand and shrink if you have the resources. It can also launch agent sandboxes, which is another part. There are reward server, replay buffer, data server, etc. running on CPUs, so you can scale these independently. Or we have disaggregated serving where we basically split the model phases into prefill and decode and send the KV cache constantly between those and scale them independently. If we have more requests, new requests, we scale up the prefill. If we don't, we scale it down. So these are trees of gangs. So it's not an easy thing to say to scheduler, you need to schedule this. This will need to scale more than the decode, etc. So TLDR, what does a scheduler have to do now? It needs to schedule a whole functional group atomically, not pod by pod, and increasingly as a trees of groups. It needs to make sure that you share the resources fairly across a team hierarchy. You should be able to borrow idle capacity from other teams and reclaim later. It needs to make room for new work without breaking what is running. And it needs to place with intent so that you're not breaking any SLIs. So you need to have topology awareness, etc. Okay, so let's start with the walls that we had, like the main things that didn't work for us in the default scheduler. So the wall number one, we needed to schedule a pod group, not a pod. So Kubernetes thinks in pods, which is completely fine because it was not created for AI workloads. So AI thinks in groups. So let me explain you why this is a problem. So when we train a model, we generally use parallelism techniques. So what is that? We either divide the data set into smaller chunks and feed it to the neural network. This is one of the examples. Or if the model is too big to fit into a single GPU, then we divide the model, like I did here. And then you basically host the whole model across multiple GPUs or multiple nodes. Or we do both, like data parallelism and model parallelism. And the scale of it can be super gigantic for some of the models. So what does that mean for us? Imagine this small distributed training workload with 8 pods. And these 8 pods make sense only together. So if only 7 out of 8 is scheduled. That means you have 0% of the job ongoing, and but you have an expensive bill on the paper. So the atomic unit has to be all or nothing. We also call that gang scheduling. And let's have a look at it, look at the default scheduler and how it deals with it. Let's say we have 4 nodes with 2 GPU on each. 1 GPU on node 1 is already taken by another workload, and the default scheduler will basically check on each pod and loop for each pod, single pod, for our distributed training job, filter nodes, scores, and binds. Okay, so 1 pod at a time, no concept of a group, and our 7th pod will grab GPUs, but this 8th one cannot. So you have got 7 GPUs sitting idle, holding a hosted job that will never start. And hence, when we say it was built to us, does this pod fit? Yes, it fits, but it needs to actually question if this group fits. And here, happy footnote, this is being right now fixed in the upstream. It's in cap 4671. Yes, I think I will. Yeah, I will link them in the recap as well. It's in alpha in 1.35 and in 1.36, and they're targeting beta in 1.37. So this was the basically first main principle that we used to create Kai years ago, and it's very exciting to see that it's getting upstreamed now. So as I said, we are using pod groups. You can only check out this part. This is how a user flow looks like for Kai. So in Kai, we use pod groups, and basically it's the atomic unit for scheduling for us. We check if we can basically schedule all of those pods. If not, we are not scheduling it, and it's pending and stays in the queue. And there is another super important point that we bumped into and needed to address, which is unique in Kai as well. Which this is the trick basically that makes all or nothing actually work in an optimal way. So we are not talking about pods anymore. We are talking in pod groups. And before taking any action in the cluster, we are checking which action makes the best fit. So we are running some in-memory simulations for Kai and seeing if we preempt someone's work, is the new job gonna be able to fit into the cluster at all. If it doesn't fit, we are not preempting any jobs. So before binding anything, Kai takes an immutable snapshot of the cluster. It speculatively places the whole gang in the memory and asks, okay, does it fit? If yes, then we commit and send the binding request to the async binder. If not, we roll back and touch nothing and check out constantly in a loop. So nothing gets bounded until the whole group is proven. Okay, goal number 2. What is fairness? How do you define it? And how to make sure pooling resources of each team actually benefits everyone? Because why would I give my resources to a pool if I can't access them whenever I want to? And how to make sure that we can share them efficiently. So if we start talking about pooling resources, as I said, the first thing that comes to my data scientist mind is having quotas for each team, because I want to access my GPUs that I purchase for my team from our budget, and I have the right to access them whenever I want to. But the whole point of pooling resources is like sharing them, right? When the others are not using theirs. So Kubernetes has this concept of resource quotas, but it's a flat and per namespace cap enforced by the API server. And it's enforced at the creation time. So if you're over the cap, your pod gets bounced at the door and never even reaches the scheduler, which is a problem. So the scheduler basically has zero concept of who owns what, and it only sees what made it past that gate. And the cap doesn't share, right? If research is maxed out while production sits on idle GPUs, too bad. No borrowing across that line, and you can cap a cluster, but you can't share a one. And one extra thing that makes life even harder is that enterprises has hierarchy, team hierarchy, departments and projects and teams, and a flat namespace cap has no idea of any of that exists. So no fair share, no borrowing, no organizational tree. So here is what we and our users actually want. We want quotas as a tree with a fair, dynamic way of sharing those resources. So every queue or team in our definition gets a guaranteed deserved quota, which is in green here. And the idle capacity around in the cluster gets lent to busy teams as over quota and split by an over quota weight knob that you can basically change per queue. And this knob decides who is going to get first from those over quota resources, and it's reclaimed when the owner is back. So for example, right now, computer vision is taking over some resources from an NLP, but if NLP team comes back after their coffee break, they can take them back. And for this, we are using a very well-known algorithm called dominant resource fairness, DRF. And the thing we see over and over in enterprises and teams is that the moment you let teams borrow dynamically, utilization jumps in the clusters and the number of jobs they run it multiplies. So that over quota pool basically ends up being one of the most used things in the cluster. So DRF is used by other schedulers or job dispatchers as well, but it has an issue. Anyone has an idea what it might be? Anyone from HPC world? Yes, you. Okay. So DRF on its own is point-in-time fairness. So it's a snapshot, basically. Look at this example. There's two teams. There's an LLM team and vision team. They're running within their quotas. So the LLM team was running in their quota, and vision team was borrowing it. So one time that LLM team submitted a bigger job, a burst job, bigger when they needed to basically train a bigger model, they could not get those resources because DRF looks at the point-in-time fairness. So this is solved by HPC World years ago. So we worked on this new concept called time-based fair share on Kai, which is a new mode that you can turn on. So it basically gives fairness a memory. If you burn a lot this week, then you get a lower over quota score, so you will get penalized. This is the same example, but this time I turned on the time-based fair share mode, so you can see the oscillation between the teams, and they reclaim resources throughout the time. This is a simulator that we have in the GitHub repo. If you want to check out and try out different stuff, you can always do that. I also used the simulator to generate these graphs. Okay, wall tree. So when someone has to give, someone needs to get preempted or reclaimed. Who loses? Let's have a look at this scenario again with default scheduler. So we have a high priority job submitted from research namespace. So the scheduler goes ahead, preempts, sounds reasonable until you see how. So problem number one. Priority is a single global order. So a high priority job will happily evict another team's work when that team is within their quota, right? That's protection with zero fairness. And problem number two, this might be a gang, right? The problem that we talked about previously. So this preemption is being done pod by pod. And it's gang blind. It will kill individual pods with no idea or whatsoever if they are belonging to a gang. So it can murder your pods and basically lets your training run hanging. So in Kai, we do two things instead. Kai is quota aware, so it reclaims borrowed capacity first and never touches the guaranteed share, no matter how high priority it is. So if it's guaranteed to you, it's guaranteed to you. And it's gang aware. So as I said with the simulator, in memory simulations, we simulate if the eviction and the placement together basically works. So it only evicts victims if the newcomer actually lands in the cluster. So we are not killing any pods without actually placing the new ones. So this is how we are doing it with Kai. Okay, the fourth one is, I think, one of the most loud topics in the community, topology awareness. So it fits doesn't necessarily mean that it's fast. So modern jobs are distributed across many nodes. And when I say many, it can be even thousands. And the pods talk to each other constantly. So where they land relative to each other matters a lot. Here's a super simple example. 4-pod distributed training job. So if scheduler only checks, do the resources fit for that job, it will happily scatter the pods onto node 1, 2, 3, 4. Resource-wise, it looks good. And that's the trap. So these nodes might not be within the same rack with high-speed interconnects like NVL72, or within the same block, or even same availability zone. So this will result in different network bandwidth between different parts of the model. So basically, if scheduler can take the topology into account, it can make a better decision and put all of those pods into the same rack. And you might think, hey, we have a concept called pod affinity. Have you ever heard about it? Yes, but it falls short. Why? Let me explain. So consider this scenario. We have another workload on node 5, and basically scheduler will go one by one. The first pod is going to get scheduled at node 1, and it anchors the placement for other pods that will be scheduled next, one by one. But since the scheduler didn't plan ahead for the entire workload, it cannot guarantee an optimal solution. It doesn't end here. As I said, we like complex things. Some new workloads like disaggregated inference has very complicated communication needs. So let's check out. Meet the cast. We have prefill leader, prefill workers, prefill leader, decode leader, decode workers. So prefill initializes the model's internal state and then passes the KB cache to decode, and decode generates the output token based on prefilled context, producing the final model result, which you see on Cloud Code or ChatGPT, etc. So this type of workload has a specific communication pattern, right? Leader and worker pods of the same group rely on high bandwidth, low latency communication to sustain model parallelism, and this is the primary networking requirement. And there is a second requirement, which is the KB cache transfer between prefill and decode. Still matters, but it's a different tier of clause, if you may say. So now placement isn't just one constraint, it's a hierarchy of them. A naive scheduling scenario could spread it all around the world, right? So you can see that pods with frequent network communication can go anywhere, and they cannot benefit from the fast inter-rack communication. And with topology awareness, you can basically take into account, okay, which group is where, and if we can optimize it for a single rack, and additionally take into account that you should be in the same zone. So we are doing that with Kai as well, and recently we also introduced NUMA-aware scheduling, which is also something important for KB cache offloading. Okay, so where is the community on all of these, and where is the upstream going? So there is some exciting stuff happening. I also linked them. I think we can share the later on presentation. So the gang scheduling is in alpha in version 1.35. There are a lot of caps happening with workload API efforts. So there is also a topology-aware cap, which is in the early state, but it's gonna land at some point. There is also another effort that we are pushing in the community, which is the two-level hierarchy in the workload API, which is in early phases, but still super important for those disaggregated serving type of deployments that people will need very soon in the upstream. So if we want to recap, these are the key takeaways that I want you to take from this 30 minutes talk. So Kubernetes kube scheduler is amazing. It was created for microservices on CPUs. It's amazing for that. But you cannot configure your way, unfortunately, to an AI scheduler. With kube scheduler, that's what we saw at least. and you need an advanced and specialized scheduler like Kai, if not Volcano, Q, etc. You need to schedule the group and not the pod. So the unit should be pod group, or however you call it, basically the gang. Sharing is caring only if the game is fair. As a data scientist, I like a fair game. And fair today is not fair this month. So you need to take into account the whole time period when you're sharing the resources. Preemption without the collateral damage is an art, and you need to a bit simulate what is going to happen before touching someone's job. And it fits is not the same as it's fast. So topology and NUMA awareness is basically a first-class scheduling dimension for schedulers. Yes, so as I said, I'm one of the maintainers of Kai Scheduler. We are a CNCF project now. Feel free to have a look at the GitHub repo. We are also active on CNCF channels. It's Kai Scheduler. We have bi-weekly meetings where we discuss issues, PR stuff, any new design, and we have a mailing list for updates. Break it with us. Come break it with us and let us know what you think. We are also looking for contributors in fresh ideas so that we can push the limits further. And one last thing before I finish, my team is working on a lot of different projects. When we push it to production, we sometimes open source them. If you are working on your own AI platform, you might find some of them interesting. They're all open source. If you're interested, feel free to check them out in case they are useful. Yes, thank you so much. That was it. Any questions, I guess? It's the last presentation. Oh, wow, okay.
Hi. The topology awareness, is that something where you can also preempt or evict nodes? Like, let's assume there's not a great fit for a whole job that needs like a good topology.
Okay, so we have two different versions. So you can prefer a topology, or you might require a topology. If you basically specify a required topology and it's not available in the cluster, it will be pending. If you prefer a topology, we cannot find it, but we can approximately find something good enough, then we schedule it. So there are those two options that you can take into account when submitting the job.
Thank you. The whole thing regarding the hierarchical quotas, so that's coming to regular workloads, not only AI-related stuff, right?
The upstream ones?
Yeah.
Yes, this is the Kube scheduler.
Okay, great.
I can also stop there in case you want to have a look at the caps contribute. Okay, perfect, perfect.
Be a newbie question, but how does this scheduler relate with Q, and what's the integration there? So you can use Sky Scheduler for Q distributed clusters as well?
That's a good question. That was something that we were discussing with the Q team, but never became a priority for any of the teams because of everything going on. So I guess if a user comes and says, hey, we want this, we will work on it at some point, but we have an issue at the Kai repo as well. We opened it, but yeah, we are trying to prioritize according to the demand. So if anyone is interested in contributing, we can also create a cap for that, just announcing it here. But yeah, that was basically what we were talking about, the Q being the global job dispatcher and Kai being the in-cluster scheduler. And them communicating. It's a big design. It's a big design, needs to be worked on. That was the initial thought process, at least between two teams. If you have any other ideas, I can take it. Okay. Any other question? Perfect. Thank you so much, everyone.